Hello everyone, my name is Boris Matijasevic and I'm here today to talk about Delta Lakes. Okay, let me share the screen. Okay. Okay, I hope that you can see the presentation. So we'll start with a little bit of theoretical knowledge because we need to understand some of the basic things before we jump to the demonstration. And I promise it won't be long, like 10 to 15 minutes, and then we'll jump to the Visual Studio Code and see everything in action. So we'll first start with a little bit of explanation about data lakes, so good old data lakes. Then we'll introduce delta lakes and we'll see what benefits delta lakes have over the plain data lakes. Then we'll see our demonstration, and then I'll explain, if you find this topic useful, how you can continue to investigate in this topic. So data lakes. We use them to store huge amounts of data. I mean, really huge. We can store terabytes, petabytes data, and that data can be of any structure. We use them to store structured, semi-structured, unstructured, byte format data. So like media files, we have images, videos, we have PDF files, JSON, CSV, tabular formats like Excel, and so on and so on. So anything that we ingest into our system, we tend to store in our data lakes because we usually don't know if that data will be useful. And if we know, we don't immediately know how we're going to use them. Then we're going to do some transformations of that data to make it useful to our business analysis later. Data lakes are really cheap nowadays because storage itself is cheap. So we can create our own on-premise data lakes, for example, using Hadoop cluster or something like that. But today we usually use cloud providers like Microsoft, Amazon, Google, and we use their offerings of data lakes. And that's all good, but we also have some challenges of data lakes. These are just some of them, not all of them. Namely, what is one of the problems with data lakes is that we tend to have a lot of very small files, and that tends to impact our query performance, because the biggest impact of query performance with data lakes is that access time, so read and write. And when dealing with a huge amount of data, that milliseconds can accumulate and then reduce the performance of overall performance of our system. Next challenges, for example, would be if I have multiple writes writing to the same file. So, you know, cloud storages are usually implemented as key value pairs. And if I have multiple writers writing to the same key, data that they want to update to that key can collide and then potentially corrupting that date. And one of the biggest issues here is that it's often very hard to know if data is actually corrupted. We really need to spend a lot of energy and a lot of time constantly verifying our data that everything is okay. We also have challenges of updating, deleting the data when we have petabytes of data and we have some regulations like GDPR or CCPA. It's generally hard to find what data we need to update in order to remove, for example, sensitive data or any other things that we need to update. So one of the things that we can use to overcome these challenges is to use data warehouses, for example. But they also come with their own set of challenges. And another approach would be to use something in the middle. So let me introduce you here to the concept of lakehouse. So lakehouse is a hybrid solution which merges some of ideas of plain good old data lakes and data warehouses. I like to say that it takes both of these worlds and mash them together. And this is where data lake comes in. Data lakes especially enable this kind of architecture. So delta lakes sit on top of our data lakes and between Apache Spark and these storage systems. So what I mean by this? Delta lakes are our asset table storage layer. Apache Spark will talk to the Delta Lake, and then Delta Lake layer will talk to data lakes. So Apache Spark is no longer directly contacting data lakes to write data into or read data from. Now we have that layer in between, and that's exactly Delta Lake. One of the biggest benefits of Delta Lake is that ACID guarantees. So we can be sure that if a transaction which is started through the Apache Spark, will either completely finished or it will be rolled back. We do not have that guarantees with plain old data lakes. Also, Delta Lakes are open source, and you can find Delta Lake is open source, and you can find the whole code on their GitHub page. We'll show that one later because I would like to show you one example of in their code. Delta Lakes use only Apache Parquet format for now. There has been some discussion in order to support ORC and other formats, and at some point of time, Delta Lake team had a configuration where you could choose the format, but that's no longer true. For now, we are only stuck with Parquet format, and it's a good choice if you ask me, and it hasn't backfired yet. I'm always saying here Apache Spark. It doesn't necessarily have to be Apache Spark. Other engines can also use that Delta Lake layer, but they cannot use it directly. Only Spark can. Other engines must use manifest files, which we can produce in our code in order to enable that engines to use Delta Lake layer. And the heart of the whole idea of Delta Lakes is transaction log. And that's what's going to be today's main point in this presentation. So what's the transaction log? First, let's explain what Delta tables are. So in Delta Lakes, we have our Delta tables. And Delta table is nothing else but a simple folder on our data lake. And that folder contains Parquet files, and these Parquet files contain our data. But it also has one special subfolder in it called Delta log. So any folder which has Delta log folder in it is called Delta table. It does not necessarily to have Parquet files if we have just created a table, but as soon as we add some data into it, we'll have Parquet files as well. It also contains some CRC files for checksums. So the idea here is that when I insert the data, for example, not only will I add Parquet files, which will contain our data, we'll also add another entry into our data log. And that's what you can see here from the right-hand side. Every time we do something on the Delta table, we'll add another JSON file. These JSON files are named in incremental order with up to 20 padding zeros. That's because we want to order them because the order is really important. These files will contain events on our Delta tables. And in order to restore any version of our Delta table, we need to replay events from this folder, from the first one up to the one where we want to stop. So if we want to have the latest state of our table, we can replay all of these events, and then we'll see what data do we have in our table at the latest state. That's important because not all Parquet files that you can see here in this folder are a part of the latest state of our table. Some of them are only a part of some of the previous states, and that's one of the biggest benefits of Delta because I do not have to go to the latest state of the table. I can stop at any point in the between and see files and see the state of that table at that version. Once all that all can get a little big over the time, so we have our mechanisms to delete, not use Parquet files, not use JSON files, but we'll touch upon that later. Delta Lake is generally very performant at dealing with petabytes of data, so that's usually not a problem. And before we jump to the presentation, the last slide, where I quickly want to reiterate over the benefits of Delta Lake. So like we said, the most important thing, ACID transactions, and when I say transaction here, I mean Apache transaction where I want to write something to our table, delete something, modify, change protocol version, so anything that I want to do over the Delta table. It is guaranteed to be ACID, so atomical. It will either happen or not. And that is the guarantee of a Delta Lake layer between Spark and data lakes. We can also have multiple writers writing to the same key, let's say, from the Delta Lake, and we are guaranteed that that data will not be corrupted because we'll have the serialized flow of transactions in the same way as if they happened completely completely if they weren't concurrent, if they happen serially, that log table, that log folder that you just see, it holds our metadata. So everything that we need to know about our files is stored in that log transactions. And it's really useful for seeing the history of our table. And we can also do data skipping and a lot of optimization that Delta Lake does thanks to that metadata. Another important thing is that, as you can see here, metadata is stored alongside the files. So not somewhere else, it's stored directly with the files. We already mentioned time travel, and whenever we have time travel, we also have audit logs of things that happened. Data Lake works with both streaming and batch ingestion of data. Data Lake enforces schema. So unlike with Parquet, where we can have a table consisting of multiple Parquet files, and these Parquet files can have different schemas, in this situation, Delta Lake forbids that. So Delta Lake has a unified schema. We can evolve it over time if we need, but the thing is, when we insert some data into our table, Delta Lake will first check if that schema adheres to if the schema of the data that we want to add adheres to the schema of the table where we want to insert that data. And if it's not exactly the same schema, the insert will be rejected. And we'll see that in action in just a couple of minutes from now. It also enables us to do operations like merge, update, delete, and all other things that would be really hard with Parquet files, because Parquet files are immutable. But here in Delta Lake, it uses some magic behind the scene to quickly create smaller Parquet files and enables us this feature. We'll also see that. And the last thing that I wanted to mention is that if you know to work with Apache Spark, you know to work with Delta Lakes because it uses existing APIs. You have multiple APIs that you can choose from. For example, SQL, we have Scala and Java, we have Python. I believe that we have R support. I'm not completely sure. And today we're going to see Python in action. Specifically, we're going to use PySpark. We're also going to execute some SQL queries using PySpark, but you can also do everything from here in Scala as well. Okay, so for the setup where I'm going to present this today, I'm going to use my local setup, which I set up on this laptop I'm presenting now from. And I decided to do like that because it's easiest for me to open Visual Studio Code and show you all the changes that we're going to do with our files. Alternative to this would be to use something like Databricks deployed on, for example, Azure or AWS. But I find it a little bit hard to list all the files and all the changes from their view there. But you can also do everything that we're going to show here from their environment as well. If you want to follow the steps that I'm going to show you now, you will need a Spark, and for Spark you will need Java. And because we said that we're going to use PySpark, we need Python, we need a Delta Spark package, specifically from pip, which will need to give to PySpark in order to be able to do operations on the Delta table. And we're going to show all this code executed from Jupyter Notebooks. It's not necessary. You can use just PySpark shell. You can create a Python scripts, which you can execute directly on the Spark. It's just easiest for me for demonstration to use Jupyter Notebooks at this point. Okay. Okay, thank you for that. Let's jump into the demonstration. So, one more thing, I'm using Windows here simply because I had a lot of problems setting up Linux virtual machines, and all of this, which I mentioned here, is a lot more easier to set up on Linux, but since I had some technical issues there, I set it up everything on Windows. Everything is going to work on Windows, but it's just a little bit harder to set up. Also, another thing, in order for Delta Lake to provide us with these ACID guarantees, it needs to have some of guarantees from the underlying storage system. So be it Hadoop, be it Azure ADLS, be it S3, Google Storage, anything. Some of these platforms have all of the guarantees which Delta Lake needs. Some of them don't. For example, local file storage, which I'm going to use now, both Windows and Linuxes, they do not have all the support that Delta Lake needs. But for Windows and Linux specifically, as long as we do not have concurrent writes into the same key, we are completely okay. So this is just for demonstration purposes. Do not use this setup for production. For production, please use something like Databricks or on Azure or Amazon or something like that. Okay. So the very first thing that we need to do is to start the PySpark session. Okay, so I'm just running the PySpark shell, which will be connected to my Jupyter notebook because I set it up as runner driver, and I also need to pass it some Delta Lake packages. We could also show all of this here in the Jupyter Notebook web UI, but I think it's, again, very much easier to show it from the Visual Studio Code, because on the right-hand side here, you can see the code. Can I? Okay. Because on the right-hand side, we can see the code, we can see the terminal, and on the left-hand side, we can see all the files that we are going to use in this presentation. So the very first thing that we need to do right now is to connect to our Jupyter session. So this is the my localhost address and the access token that I'm going to use for the connecting. Okay. And we'll select Python 3 kernel from the Jupyter notebook. Okay. And to verify that all this works, we are just going to execute this first cell. And if it works, I'm going to explain what's happening. And it should work. The thing is, okay, so we have established our PySpark session. We can now minimize the console, and we can see the output of our first cell. So throughout the demonstration, I'm going to execute a lot of cells here and explain everything that's going on. And we'll see the changes to our Delta tables and specifically to our Delta log, because that's the point of this demonstration. So here by PySpark, we are granted the default Spark session, and it's stored in a variable called Spark. We can use that one. We can create our own session. I'll use the built-in one. Really no need to create another one, especially because this is a local setup. And as you can see here, I have one master node for our Apache Spark, and I'm using the version 3.4.1. I guess that some of you know that there is a later version which came out like a month ago, I think, but this version is like from April of this year, and I didn't really have enough time lately to check the newest version, so I guess that some things maybe improve over the time, but by no means is the version that I'm showing you here old. It's just like a couple of months old, so don't worry about that. Like I said, this is the execution of the first cell. We've seen what we have in our Spark variable. Let's go to the next one. So I want to start this by creating some in-memory data frame. The data frame will hold just basic information about the people, and we'll use people Delta tables throughout this whole presentation. So our first data frame is going to contain information about 5 people. We'll use ID, first name, last name, and age, where ID and age will be integer types, and first name and last name will be of string type, and all of these will be nullable. It really doesn't matter. This is just a very simple example that I wanted to show. You can use any other formal schema. But the important thing here is that I want to have clearly defined schemas. So I create from Spark, I'll use their API to create a data frame with this data and the schema that I just specified. And let's execute this cell. This is so far, this is only happening in memory. The first output will be the schema of the data frame. So we defined it here, and we can see it printed out here. That's exactly the same information. And another thing would be to actually show the contents of a data frame. Let it not worry you that this was executing for 17 seconds. Like I mentioned, this is just my local setup. It will be tremendously faster on any production-ready cluster. So no worries there. And as you can see here, this is the content of my data frame, our 5 people stored here. Okay, now that we have this data frame in memory, let's store it on our hard disk, for example, using the Parquet format for now. So if I execute this cell, you will see on the left-hand side that now I have a folder called people Parquet, because that's how I name our table here. And once this is done, we'll be able to see the contents of the Parquet files. For the Visual Studio Code here, I have installed an extension which allows me to see the contents of Parquet files. For example, if I open this one, I'll be able to see its contents represented as JSON file. So Parquets are generally binary files, and when you open them like this, you won't be able to see anything here, just some byte gibberish. But thanks to the extension here, we can see actually the data here. So we can see these all Parquet files contain our data. And we have a success file indicating that writing to this Parquet table is successful. Now let's try to write the same data frame to our delta table. And as you can compare these two cells, the only thing which is different is that you need to specify from format Parquet to format delta. And I need to do this only here on my local cluster, local setup. On Databricks, for example, a long time ago, they changed that delta is now the default. So on Databricks, if you go to write data frame right and just do the save, you'll get it automatically outputted to delta format. I forgot to mention, Delta Lake was created by Databricks a couple of years ago, but since then they open sourced it. And like I said, you can find their source code on their website. Also, I want to show you something really quickly. Delta Lake cheat sheet. So all the comments that I'm going to show you today, or at least majority of the comments that I'm going to show you today, you can also find in this very handy cheat sheet from Databricks. You have 2 sheets here. First one is for SQL commands, and the second one is for Python commands. We're going to use commands found in this Python section. We're not going to use all of them. We'll also add some of our own, but this is the gist of using PySpark with Delta Lake. Okay, let's get back to our demonstration. And for our delta table, you can now see that you can see what's different from the Parquet table. We no longer have these success files, but we do have transaction log, which is stored in our delta log folder. So this people delta is now considered a delta table. We also have the same Parquet files here, okay? And in delta log, we'll have only a single entry here. So let's explore that one just real quick. This is a JSON file, but it contains multiple JSON elements in the root of the file. That's why Visual Studio Code is complaining here that the syntax is not okay, but it's completely okay. If I format this file, we can more easily see the sections that it contains. So we can see Unix timestamp when I execute the creation of a table. We've seen the operation. So it actually says here right because we've written this data frame into the table. We didn't just create an empty table. And we're going to do that in a couple of minutes. I'll show you that as well. It would error, for example, if the table already existed. We also have mechanisms to say, okay, if table exists, don't do anything or replace the table. It shows us the number of output files, not the number of output rows. So we have 6 Parquet files, and that's true. You can see here. And in one of them, we do not have any data. Spark just created a little like this. I'm not completely sure why. Probably something due to parallelism. And we have 5 rows because we have 5 people. With engine Delta Lake, transaction ID. This is the ID of a transaction of a client which executed this command, and we're going to talk about this at near the end of the presentation. We're going to talk about protocols also near the end of presentation, but you can think of these as table features. So the larger this number here for a reader version, the more features readers must and will support from the delta table. Also the same thing for the writer versions. We're going to mention some of that feature later. And this is the metadata for this specific commit. So yeah, let's get to the terminology right now. So every JSON file that you'll see here presents a commit. So commit is equal to a version of a delta table. And every version is also called a snapshot. So if I want to go to the version 3, for example, I'm going to time travel to the JSON name 000 then 2.json. And that will be the snapshot at the commit version 3. Very important thing here, so we have ID, but very important thing here is the schema string. Here you can see the exact schema that all the files that I'm going to try to add to this delta table is going to have to adhere to this schema. So we have ID of a type integer, which is nullable, which currently doesn't have any metadata. And so on and so forth for all of other columns, all 4 columns I believe that we have. And now this is really the heart of transaction log. So the actions that happen within a specific commit. If you have ever encountered, for example, event sourcing architectural pattern, you'll find this very similar to that. So in every commit, we're going to say, hey, we did these things in a commit. In this specific commit, we added 1 Parquet file, 2 Parquet files, 3, 4, 5. And you can see all of these files that we have it right there here. So for example, this with the part 15, that's this one. So these files now consist, let's say, for the version of a delta table, when this commit is created, these are the files which contain data for that version. They also have their stats, and this is really useful for data skipping, because when we have gigabytes, terabytes, petabytes of data, we can skip a lot of data and not scan entire Parquet files, because Delta Lake keeps track of which data is stored in which Parquet files thanks to these stats. Okay, so this is our first commit. Let's close this one and continue. So, so far, I've shown you how we can store data frame in Parquet format, in Delta format. Now, another thing, we can also convert an existing Parquet format to the Delta table. And let's do this quickly now, just to show you the example. Okay. So I have this delta table now in memory. I convert it to data frame and display it here on the screen. But also, if you now go to people Parquet, you can see that the only thing which is different now is this delta log subfolder. Success is also there. Parquets are not touched. None of the things besides the transaction log is touched. But now we have the JSON file with the operation convert. So it's no longer write, it's now convert. But all of other things is the same, because we converted the existing Parquet file to the Delta table. Very important thing, if you ever decide to go back from Delta to Parquet, the only thing that you really need to do is to just delete this Delta log file, Delta log folder. So all metadata, everything that's needed for us in order to restore, to reconstruct the state of a delta table is stored in this delta log. Once we delete it, this becomes plain old Parquet collection. Okay. And you can convert it again, back and forth, whatever you want to do. Another way to start with delta tables is to create one from scratch. We can do it with delta table class, and this will be our entry class for majority of our operation during today's demonstration. Nice thing about this is that we can define schema right here. So instead of going through the data frame and then writing to the non-existent data table, I can now define an empty data table with schema. So I'm saying, hey, let's use ID as integer, first name as string, You can also append some metadata to the columns. So for example, you can say, hey, this last name, let's say it's also a surname, depending on how you would like to call your last names. And we can also append some metadata to the table itself. For example, we can add a general comment to the table saying, hey, this is table with people data. We want to store it to this location, and then the execute. And this is just a build a pattern, and until you say execute, nothing really happens. This is a good time to talk about two different kinds of, let's execute it. So we should mention at this point that there are two different kinds of delta tables. There are managed delta tables and unmanaged delta tables. The one we created here and the one we used so far are unmanaged because we specify the location to Spark when it should create, where it should create the table. Another approach would be to say here, let's do to say table name. And here in the table name, I could specify the name of the table, and then I would just omit this location and I would execute that expression. And then in that case, this table will be stored in metastore from this Spark session, and we will not be able to see it in a location. No, let's say we won't know upfront where that location is. So for these demonstrations, since I want to show you all the files where they are, I'm going to use unmanaged tables. But for the most of time on Databricks or any other cloud platform, you'll probably use, if it's a smaller project, you'll probably use managed tables because you do not really care about the physical representation of a delta table. But if you're going to use some third-party storage like ADLS or S3, you're then going to specify the location here and store the files at that location. Delta is smart. Delta knows by the start of the protocol here. So if this was AWS, Azure Data Lake storage, I will have a protocol prefix here. If it was S3, I would also have protocol here. And using that protocol, Delta knows specifically on which storage system I'm writing to, and needs to know and knows how to tweak some settings which are used for storage layer. So here it knows that I'm using a local file system, for example. And let's check our table. So our table is now called only people, and we are going to use this table till the end of the presentation. So this will be our main one. And as you can see here, we do not have any Parquet file because we haven't still added any data here. And if we open this JSON, we now see that the operation is create table. If we expand this, we see that we have a create table. We also have a description. This is a description from our comment here. And again, engine info, transaction info protocol, more on that later. And we have our schema. This is a Parquet file. Like I said, this is not configurable anymore. This has to be Parquet now. We have our schema, and we also have, let's find it. For a last name, we have metadata now, and one metadata is a JSON format, and now we have a key with comment and value of surname. This is coming from here. Okay, so that's our empty delta table. Let's now do stuff with it. The very first thing that I want to show you now is that we still have this data frame, remember, with PyPeople from here. Let's now append that data frame to our delta table. Okay. It's now adding the contents of data frame as Parquet files to our delta table and writing to delta log. So first, it is going to write. We could have actually seen it, but okay, I'll show later. First, it is going to write Parquet files, and then it is atomically going to write entry in delta log. That way, if something crashes in between, if something crashes while adding Parquet files or after adding Parquet files, but before updating transaction log, those Parquet files will not be considered as a part of delta table, even though they are found in a folder, which is a delta table. So never think that all of Parquet files that you can see here are a part of this delta table. We even have an example now. This Parquet file contains nothing, and it is not a part of this delta table. And I'll show you later how we can remove unused ones. So as you can see now, we have, this is our first entry where we created a table. And this is now our second entry with write operation. And five of our Parquet files, which are now added to this delta table. If we move on, I'll show now how you can get the reference for the delta table. Again, we'll use delta table class, we'll specify our Spark session, and we'll specify the location of our delta table relative to the execution environment that we are executing this Jupyter Notebook from. And this is the content. This is the current version of our delta table. It contains 5 people, and you can see everything here. So we read the contents of delta table in memory, and now we're displaying the contents of that data frame. So we are converting delta table representation in memory to a data frame, and then we are showing it here on the screen. Okay, let's collapse this for a second and see the details of our table, current details of our table. We can see that format is delta. We can see the description. We can see the location where it's stored. You see the file here is the protocol used. So that's why that's how delta table knows that it's being operated from the local file system. We have our timestamps. We have size, minimum reader versions and writer versions. Again, more on that later. And current table features. These are just some table features which are enabled by default, but when we increase reader and writer version, we are able to add some of more, let's say, advanced table features. And we're also going to showcase some of them. But for now, I would like to reiterate that delta table stores all of its history. And we can see that history by running history method here. And you can see that it now consists of 2 versions. So we had version 0, where we created a table. We also now, the most current version is the version 1, where we wrote that data frame into our delta table. So you can see the operation. Here you can see the, come on. Okay. You can see operation metrics, you can see engine info. We haven't added any user metadata. I'm also going to showcase that later. So this table is, this view is really going through the transaction log from here, and it's just displaying the most useful information to us. This is going to be very useful for our time traveling later. So in order for me to show you time traveling, I first need to modify a bit our table. So I mean to simply create some different versions, and then we'll see how we can check previous versions and how we can restore a table from some previous version. For example, if we made some mistake and we want to roll back the changes, we can do it very easily with the delta tables. Okay, so let's create another data frame with completely same structure, but now we just want to add 2 more people. We'll add Zara and Kaden here. So let's first create it in memory, and then let's append it to the delta table. Okay. Once I do this, it is going to write, you've seen here probably, it's now written, excuse me, it's now written new Parquet files. And after all of these Parquet files are written, which are needed for new people, Delta updated transaction log. So only after this entry is here, we can deem that our table is now in version 3. So this is first version, second version, third version, and because it starts with 0. Here we've already seen this format. This is just a write operation with 2 Parquet files added. Okay, now let's do the opposite. Let's remove some people from the table. For example, we want to remove people which are older than 40 years. So let's execute this one. So I have a reference to this delta table in memory. I do not need to grab it every time, but I need to do sometimes I need to grab it if we change, for example, schema or some important metadata. For this DML operations, we do not have to. So from in-memory representation, I want to delete people older than 40 years, and then it's going to be written directly to the delta table with the operation called delete. And completely opposite from the write that we had here, delete only contains 2 entries which are removed. because we removed those two. They were previously stored in, not those two, sorry, but the two ones which are older than the 40 years. One entry was in this parquet, another entry was in this parquet, and both of these got removed. But they only got removed from metadata. So these parquet files, so for example, this one is 15.8.9. Okay, it's this one. We still have it here, and we can see that it was Anders, which who is old, who is 45 years old. This particular file is still here because we want to keep it, because we want to be able to roll back to this version. But if I check the latest state of this table, we would not see him shown here because we removed it from the latest state, but we have not removed him from the history. Now, going forward with the same idea, we can also update. So we've showcased here append, we've seen remove. Now let's see the update. For the update, we have update method. And the first thing that we need to specify is who are we going to update by specifying a condition here. So let's update the person with ID 6. Let's show the current state of the table here. Why not? None of table to the frame. So let's just see where are we now. Okay, so this is the most current situation with our table. At this point, let's, for example, update the ID of 6. So Zara is here, and we want to change her first name to Lara. Why not, really? I just wanted to do some update here. And if we do that, you'll now see that a new parquet file appeared here. And we see operation of update. And we have one remove and one add. Why is this like this? Because parquet files are immutable. We cannot update the existing parquet file. So what Delta is going to do, it is going to remove from the metadata existing file, which contains Zara, and is going to add a new parquet file containing Lara now. And we can see it here. Okay, so this is Lara, and this one was Zara. Yeah, okay. So that's how Delta Lake is going to do the update. And if we execute this again, we can now see that 6 is now Lara. Okay, let's now show the history of the table. So the first display here that I wanted to show is a version. So we have 5 versions which correspond to these JSON files here. And we also have their timestamps. I selected just version and timestamp. Other information is not useful to us currently. So for every version, we have a timestamp when that version is created. And that's important because there are 2 ways to time travel in Delta. You can either go back in history using version or using timestamp. And this is just the current situation of the table displayed again. So let's showcase the time travel. Like I said, we have 2 possible ways how we can travel. First one is to use version. So from this table here, let's actually see. Let's actually see the whole history. It will be easier to follow. Okay, yeah. So we have version, we have timestamp, operation, and other metadata here. So for example, let's say that we really didn't want to do this update here, or this, let's go with version 3, why not? And if we execute this line now, we'll see that sorry, I should have explained the command first. So it's just a regular format delta, but instead of just loading the table, I said here version S of, and I've now specified the version where I want to go back to. I'll also be able to use timestamp the same way, but just I'm not going to specify the version here. I'm going to specify the timestamp. But as of version, you can see that now instead of Lara here, which happened in this update, I now have Zara, and I'm able to go back to the version 3. That's this state. Remember, in this state, all the thing that we did is that we deleted people with over 40 years. But this update never happened in this version. Similarly, I can even show you the state of a table which happened before the deletion. And in this case, we have Anders and we have Caden as well. Okay, but this is just in memory. So if you see, I'm capturing this data into our data frame. The same thing goes here. Let's grab a timestamp. For example, again, if I want to go back to the version 3, but using timestamp, I'll use something like this, and I'll input a timestamp, which is between this one and this one. So let's just increase 1 second from this timestamp. For example, like this. And this is time traveling using timestamp. And this is again version 3 of the table. But like I said, this is just in memory. If I really want to restore the table into this version, I need to call restore to version table. For now, this method cannot accept timestamp. This method can only accept the version. But what you can do is you can go to the timestamp, if you have timestamp and you want to do it that way, retrieve the version for the timestamp, and then go back here and insert that version here, and then revert the table. So if I do this, so I'm grabbing the reference to the table from my hard disk. I'm restoring the previous version. I'm showing you the new history and showing you the state of a table. So the state of a table is just what we would expect. It's just without that newest update that we had here. So without Zara becoming Lara. But what happened is that maybe contradictory to what you thought it would happen, this one didn't got deleted. This one is still here, but we have a new version with operation restore. We can also see it from the transaction log here. So the operation is restored, and it literally undid what the previous version 3 did. Okay, and this works something like this. So let's use the paint really quick. So I have version 1, version 2, version 3, version 4, and for example, we are here at this point of time. I want to do a rollback to the version 3. So 4th is not getting deleted, but what is happening instead is that I'm getting now a 5th version of my table, and now the history is here. This one still remains, so this one is not deleted, and from this point I can now go back. I can literally revert the rollback by going back to the version 4. So you can see how Delta Lake is really powerful in allowing us to correct any mistakes that we made. And it will also make some guarantees to help us not to make these mistakes in the first place, which you will see momentarily when we start talking about schema evolution and schema enforcement. So this is about time traveling, and you see in this table we have the whole audit trail for our table. By default, I think that these are kept for 30 days, but it's configurable. We can configure for how long this table is going to be stored, and you can set value to some like hundreds of millions of years, practically making it for eternity, if you want. Let me just see one thing. Yeah, okay. So before going to the schema enforcement, let me just talk about this specific file here. So at arbitrary points of us playing with Delta table, our PySpark here, or let's say our Delta table client, is going to create these checkpoint files. So these checkpoint files are a part of Delta log folder, but are not stored in JSON format. They are stored in Parquet format. And these are the checkpoints. Let's say this compresses everything that happened before it into a single file, and it makes it as a Parquet file. So how Spark restores the latest version of a table? It will not go back from the zero, for example, because, for example, we can have like millions of these JSONs here. It will find the latest checkpoint. And how is it going to find it quickly? Well, we now have this file here called last checkpoint. So the very first thing that Spark is going to do is to check last checkpoint here and find the version which is mentioned here. So here it is stated that the latest checkpoint is at version 5. Okay, let's find the checkpoint. We only have a single one here, but we'll have more of them later. But let's find the version 5. Okay, this is the checkpoint at version 5. And this is a state of our table, which happened up to a version of 6, because we start with 0 here. We'll see the operations needed here to restore the current version. And these are not all the operations. If you would do a sum of all of these, you will not find them all here, because Delta tries to be as efficient as possible. For example, if we added a file and then remove the file immediately after that, this checkpoint is not going to contain the entry for that file, because we added it, we removed it, we no longer need it. But if that file is still found in the interval where we can go back in time, it's also going to be stored in this checkpoint file. And that's why we have these removes here. Once the files go out of scope from our time travel, you'll no longer see them mentioned even here in remove sections. And thanks to this being in Parquet format, Spark can very quickly analyze this file. It can parallelize its analysis and very quickly get up to some point in our table. And after that, all it remains is to process the further log and create the state that we want, usually the latest state. Checkpoints are not mandatory. You can dictate when they are going to be created, but it's a good idea to create checkpoints often so that our driver does not have to go through a lot of JSON files in order to restore a particular version of our table. Okay, so that's one of the optimizations that Delta Lake does for us. So we mentioned schemas for Delta tables, and let's demonstrate that right now. This time, I'm going to create a data frame tree, but this data frame is going to have a little bit different schema than what we had previously. The tricky part here is this struct field, this string called city. And by this, I just want to represent where these people live. So Opal is going to live in Belgrade and Liliana is living in Novi Sad. Okay, and now what would happen with a regular Parquet file is just that it will be created with a different schema. And you know, in that footer of Parquet file, it will be metadata with new schema. And then when we read all of these Parquet files together with Spark, for example, undeterministic things can happen, because Spark only checks the metadata from the first Parquet, and it assumes that's the metadata for all other Parquet files. And if it happened to read some of the previous Parquet files first, we would not even see the city in for these two people. And if it happened to read this one, we would only see nulls for the previous one once. So maybe we want that behavior, maybe we don't. Usually we don't, because that means that our data is dirty. Those two things should not go together because their schema is different. Maybe we want that, depending on our system. Sometimes we don't. And in that Delta Lake, we definitely don't. In Delta Lake, we want to have a strong consistency for schema across the whole table. So let's create the data frame tree with this data, this schema, and let's try to append it to our table people. And as you can already expect here, I added try except cases because it's not going to work. And here's the exception. So it says that there is a schema mismatch detected. Table schema is this. So in table, we have ID, first name, last name, and age. And the data that we're trying to input into the table has ID, first name, last name, age. That's the same, but we now also have city. So what Delta is suggesting to us now is to say, hey, in order to merge these two, you need to enable merge schema settings. And that's what we're going to do. So we're going to execute completely the same command like we did here, but this time we're going to mention the option of merge schema. What is this going to do is that it will allow schema evolution. So Delta Lake will see now that these new files are compatible, and it will allow the insertion evolving the schema. So let's show this as well. And what you probably expect here to happen is going to happen. These two new people will have their cities associated with them, and previous people will have nulls for their cities. So yeah, but we are guaranteed to see this. We no longer have to check for all Parquet schemas, see if they match, and be very careful with what we do. This burden will now fall to Delta Lake layer to ensure the schema enforcement. So this case that you've seen here, this is a case of schema evolution, and the thing you've seen here is the case of schema enforcement. You can actually turn off the schema enforcement if you want, but that's really not recommended. You can do it if you want, I mean, as a shortcut, instead of writing a merge schema to every statement, you can just turn it off, but it's really defeating one of the biggest benefits of Delta Lakes. But you have that option. For a lot of operations in Delta Lake, you have option to turn them off if you don't like them. Okay. Now, yeah, that's everything that I wanted to mention about schema. Actually, one more thing. So you've seen here that I did append. There's also one more option here. We can do override. We can override data. We can also override schema, not only merge schema. So that's really a destructive operation where I say, hey, I do not care about these specific people if I use predicate or the whole table about people. I just want to replace existing data with new data, and that's it. So we can do that as well if we have a use case for something like that. Let's showcase the commit metadata. So we can add some of our human readable comments to our commits if we want. For example, we're going to create data frame 4 with now new schema of city. And I'm just, the only different thing that I'm going to do this time is to set some metadata to anything that I want. This is just a sentence in plain English that I want to describe this commit. For example, similarly like you're going to do with Git commits. And whenever you replay the history of the table, if you use this option, you can see the comments for all the commits that you've created in the Delta table. So let's see this one as well. We've appended the person with ID 10. We've appended John. John is here. And to check this commit info, we can either print the current version of the table, or we can quickly go to the newest commit in our transaction log and see it. So you see now here we have user metadata and we have info here. I just said, I don't know why I said human readable. This can be human readable. It doesn't have to be. You can write anything here and it can be read by any reader in our system if we want. Okay. The last transformation of data that I want to show you is a more complex case of upsert. And upsert here is done using the merge. If you don't know, upsert is a combination of two operations of information of update and insert. So you have this up as update and insert as the last part of word insert. And it works something like this. I'll create the same schema, a new data frame this time, and I'll use two people here. But this one, we already have. We already have a person with ID 8. It's Opal here. And we do not have a person with ID 11. That's our Anna now. So you see, we stopped at ID 10. Okay. So what we want to do is say, hey, if I already have this ID, let's update the entire row or just a part of the row. I'm just showcasing now the whole row. And if I do not have this ID, as in this example where I do not have Anna, I'm going to add Anna to our table. I do not have to specify the city here because I've said that all the columns are nullable. Specifically here, city is nullable. Okay. So let's create the data frame. And then we'll say for our existing delta table, which is people, we want to update it. So that's the destination, and the source of this update is going to be this data frame, which contains update. This can be, for example, we can have another delta table and we want to merge them. We can do so in this way. We can also create in-memory data frame. We can convert that delta table to data frame, for example, and merge them that way. You can do anything you really want. This is the way to address destination table in our expression. This is a way to address the update, the source in our expression here. So what I want to say here is, first in merge, how am I going to merge this table on which keys? And I said here that only IDs are my keys here. So this means whenever you find matching people IDs with IDs from this updates data frame, I have a match. Otherwise, I do not have a match. And that's important because you're going to have a couple of sections here. First one would be what happens if I have a match. And the second one would be what happens if I do not have a match. This is not the definite list of things that we can do with matches. What I'm going to do here is, if I have a match, I'm going to update it. If I do not have a match, I'm going to insert the data. You have more options here. We can say, for example, insert all. Not listed here, but I know that we have like 5 or 6 different options. You can check in their documentation. I'm also going to show you that a little bit later. But yeah, we have a couple of options here. So when we are matched, let's update. So ID with ID, first name with first name, etc. And when we are not matched, let's just insert the data. So ID will be ID, first name will be first name, and so on and so forth. And then after this operation is successfully executed, let's see the current state of our table. I just ordered here by ID because I want to show you that, to more easily show you that person with ID 8 is now going to be Jordan, and we're now going to have Anna inserted at ID of 11. Yeah. As you can see here, at the position 8, we now have Jordan, and at the position 11, we now have Anna. Just a quick note, this ID here is just a regular column. There's really nothing specific to it. Delta has a mechanism to create auto-increment table columns, as well as auto-computed table. For example, I could have created a column here saying, for example, full name, and then I would do so by concatenating first name and last name, and Delta Engine would do that for me. I wouldn't have to specify that column all the time. That's done with generated columns as well. We also have, like I said, identity columns. That's how we can auto-increment a column. Okay. So that's about the DML operations over this table. Now, if you go and check this Delta table here, so we have a transaction log, and we have all the Parquet file which we created during this whole demonstration. And we have like, I don't know, like 15 of them, for example, here. But imagine that in a production system, we could have like 1,500, thousands, millions of this Parquet file. Particularly if we are using streaming, we tend to have a lot of very small files. And if you remember from my presentation, I said that one of the biggest performance issues, both for data lakes and delta lakes, is that huge amounts of files, a huge number of files which are very small. Delta Lake likes big files, not so many big files, but it hates a lot of small files because milliseconds add to the overall delay of the operation that we want to do on the delta table. And of course, delta table has a way of dealing with that. And that delta table has this optimize operation, let's say, and we can optimize a couple of things. One of the things that we can optimize is the compaction of Parquet file that we are using here. What compaction means is that Delta Lake is going to take the version of a table that we are currently at, and it is going to create much bigger Parquet files and as few as possible. I think it's possible, I read in documentation once, it's possible to influence actually the size of Parquet file and number of Parquet files, but they've done some extensive research, and I think that they've said that Parquet files of up to 1 GB is industry standard for optimal performance. So in most real-world use cases, you will not tamper with the algorithm that Delta Lake team has set already as default. So that's exactly what I'm doing here. I'm just saying, hey, Delta, let's please optimize this table by using a compaction and do your magic behind the scene. Okay, so we now see that this is just the result of operation. We can now go to the transaction log and go to the latest entry. And latest entry will now have the operation of optimize. We see that we remove all of because these are very small Parquets in our example. It logically removed all of them and it added just one big. So this one is part 0 and it's EF8. Let's find it. Okay, so now you see that we have only one Parquet file with all of our entries in this one. And Delta Lake will, Spark will ingest this Parquet file much with much better performance instead of us loading a lot of small Parquet files. Okay, this is a trivial exception, but like I said, you can imagine that we have terabytes of data with millions of or billions of Parquet files. Now comes the question, since I have everything here in this Parquet file, do I really need all Parquet files? Well, the answer is yes, if I want to use some of the features from Delta table, for example, time traveling. But if I do not want, I can use the option called vacuum. What vacuum is going to do is that it's going to check the current version of the table, and it is going to remove all Parquet files which are no longer needed. And if you recall from the last operation, really the only Parquet file that we need is this one. So after I execute this vacuum, you'll have a warning message showing up. You have also to disable some checks here because this is a destructive operation which cannot be rolled back. Once the files are deleted, these are deleted. And this is the very first operation which is going to actually modify the state on a physical drive, which we won't be able to restore. So as you can see here, the only remaining Parquet file that we now have is this one with all the data. And our data is still present, everything is fine. We have JSONs here representing the history, but we do not have this Parquet file from these files. If you would try to go back in time, for example, to this version here, Delta will see the metadata which happened up to the version 7 here, and it will see that some of the physical files containing the data is not present, and it will throw an error. Okay. So that's the end of our people table. There is one more thing that I want to show you, but I'll create a new table for this. I just don't want to tamper with this one. No specific reason. And that's protocol versions. If you recall from our first commit here, we can see that we created this table with operation create, and we had this protocol part here. This protocol is the version of Delta protocol, and it has two subparts. First is reader, and the second is writer. And this is represented by something like this. This is literally the JSON that we took from there. But now I just changed the reader version to 3 and the writer version to 7. Why? Because this is the latest, this is the most up-to-date version of our readers and writers that we can use. Version 2 adds one of the features for readers. Version 3 adds new ones as well. The same goes for the readers. In their documentation, you can see what every version adds new. But they've decided to stop at version 3 and version 7. And instead of incrementing these versions, they've said, okay, let's no longer increment them, at least for now. Let's add something which is called table features. Table features allows us to have arrays in JSON like this, where we specify independently features for readers and writers. You can see that I'm using now column mapping here, both for readers and for writers. And for writers, I'm using identity columns. For example, identity columns we have already specified, and that's the feature of Delta Lake, which auto-increments some columns. We need to know about that logic when we are writing the Delta table, because that Delta table has to have new row with incremented value, but it doesn't have to be aware of that during the reading. For reading of that table, that's just the plain column, nothing really specific to it. Column mapping is a feature which is often used. It allows us to decouple the actual names of columns from Parquet file, between Parquet file and metadata. For example, you see that here I have column ID in Parquet file, and also in schema. We didn't involve, so we can check the first one. Also in the schema, I have this name here, ID. But if I want to rename the column or drop the column or reorder columns, I would need to, if I weren't using Delta, I would need to recreate the Parquet files here, which can be really expensive. By using column mapping, I can decouple these and I can only update the metadata, and then a new name in metadata is going to point to the old name in Parquet files. Not only that, this also allows us to have some invalid characters, some characters which are invalid for column names in Parquet. Delta now accepts, because this is just a JSON and you can input any name that you want here. Okay, so let's showcase this as well. Let's copy our Delta table to a new destination. I'm doing this here simply by saying, hey, let's read the old table, copy it to data frame in memory, and let's just put it in a new place. There is a smarter way than doing this. We also have shallow and deep copies, but I just didn't showcase it here. But you also have an API for copying the table. So if I do not have any features enabled on a table, and I didn't evolve reader and writer versions, I could do something like this. I could say, hey, let's load this table. Let's rename the column from last name to the surname, and then let's overwrite that to the existing table. You remember probably that I said not only can we append, we can also overwrite things. And once I execute this, so remember, I didn't enable column mapping for this table. Once I execute this, we'll see that we have a first version which had last name, and a second version which had surname. And imagine now doing this with millions of Parquet files. It was easy now to do with a single Parquet file, but it would be a very expensive operation if we had to overwrite everything for millions of files. So let's not do that like that. Let's do it in more smarter way using table features. So let's recreate this table. And now we're going to use, this is example how you can run SQL commands. Some commands do not have Python API support yet, and I think that SQL is the most complete, but it's like 99%. So this is just an edge case where we need to use SQL to enable column mapping. And you can execute any SQL by saying your Spark session.sql and then pasting here your SQL query. We could have literally done all of this demonstration using SQL. For example, not saying load, we could have said select star from our table. So what I want to do here is not select, but alter. I want to alter this table to enable column mapping. There are several modes that you can use. We're using name here. So enable column mapping. And in order to do that, I need to increase the reader version to 5 and writer version to 2 and writer version to 5, because this feature concerns both of these versions. And after I do that, I want to rename the column from the last name to the surname. So here, I only have one Parquet file. Once I execute this, the column, at least in metadata, is renamed. But here in data, we didn't change anything. It's still last name. But here, in the latest commit here, we can see that we did a rename column, and the input parameters are, okay, let's rename from the last name to the surname. And if I go here to the schema, you will see that now it's no longer first name, it's surname. Okay, here. And that's how Delta is able to reconstruct the latest schema only from the metadata. And it allows us to have different column names from what is found in Parquet files. We can also see what's currently enabled on the Delta table by querying table properties. Remember, we here altered table properties. Here we are querying Delta table properties. We can see that we've successfully increased our versions, and we have enabled column mapping. Column mapping is far from the only option that you can do with versions. You can have, for example, delete vectors. Delete vectors allows us to you have a big Parquet file, and you only want to delete a couple of rows from there. What we would naturally do is to create a whole new Parquet file and only omitting the data that we wanted to delete and specifying that as the newest version of Delta table. Delta protocol actually allows us to do in a more smart way. So the only thing that Delta would do in that situation, if we had deletion vectors enabled, is that it would create a new entry here in transactional log stating, hey, when you read these Parquet files, please omit these rows. And that's it. No rewriting of Parquets, no doing any expensive operation, just adding a small JSON file to the transaction log. And yeah, that's everything that I wanted to show you here with a hands-on situation. And before we conclude, I would like to show you one more thing. So this is the list of some of materials that if you found this presentation interesting, that you can check and continue researching here. So like I said, the whole Delta Lake is found, the whole Delta Lake, sorry, is now open source, and its source code can be found on GitHub on this address. Also, the majority of things that we spoke now can be found in entry. This is textual entry for the transaction log itself. I mean, we can check it really quickly. This is a huge file containing everything about the transaction log in Delta, yeah, and they're constantly evolving this file. So whenever they add something new, this is a single source of truth of documentation for transaction log in Delta tables. So you can check this one. This is their homepage. This is now a part of Linux Foundation, and you can check the docs here. Docs are really great. They often showcase both PySpark and SQL interfaces. They usually have even the Scala, Java, and other kinds of APIs, and they show how you can do the same thing using different approaches. This is documentation which we just seen, and if you want to know nitty-gritty details about the data lake and how it came to be, and more benefits and more issues that they solve with this, you can also read their white paper on this topic. This white paper has 14 pages, and it goes in all of the details that you need in order to understand the Delta Lake. For example, one very interesting part, at least to me here, is the sequence of actions that Delta does when reading from the table and when writing to the table. And you can see that we mentioned already here. So when I read the table, I need to find the last checkpoint. I need to list all the JSON files, reconstruct the latest state. And the hardest part for them to implement all of this is this one. So the fourth step of writing, because it needs to happen atomically. This is the part when we write a JSON log entry into our transaction log. Here, they rely on underlying storage APIs to do atomic things for them. Sometimes it's easy. Some of these storages provide that, some of them are not. And for some of them, like for example, for Amazon, currently, at least at this point, they needed to deploy some services behind the scenes for us, which will enable these guarantees, which S3 does not by default. And you can see details of that here. They also explain if you want to deploy on your Hadoop clusters, what they needed to do in order to support Hadoop, etc. So yeah, I believe that's everything that I wanted to showcase today. So thank you everyone for your attention. I really hope that you find Delta Lakes amazing, just as much as I do. And please do not hesitate to reach out to me if you want to discuss this or any other topic further. And if I'm not mistaken, you will have access to both of this presentation and the Jupyter Notebook file that I created, so you can play with this for yourself and have just a small cheat sheet to start with. So yeah, thank you.
Thank you, Boris. Thank you for everything. Thank everyone for participating. We enjoyed, all of us.
To get some water and
Bye.
somebody